Hello student, to the Foundation of Classical Electrodynamics course. Under module 2, today we have lecture 42, and in today's lecture we will going to calculate the energy stored in a capacitor and try to and start the discussion on the dielectric. So, we have class number 42. So, in last class we started our discussion on the capacitor. So, we have two parallel plates where we know the charge are distributed, and some negative charge is here. And then we have the electric fields, that is in this direction, sigma divided by epsilon, that was the value. Okay. And then we calculate the capacitance C, that is that we calculate as, by definition it is Q divided by V, and we find that this value is essentially epsilon and multiplied by A divided by D, where D is a separation, this separation from here to here, and A is the area of the capacitor. The standard parameter for this for the capacitor is this. So, now today we are going to calculate what is the amount of energy stored in this capacitor. So, the concept is like this. So, suppose I am having a parallel plate capacitor, these are the parallel plate, and where you have the charge is this negative charge like this. So, the point is, to charge up a capacitor, one has to remove electrons from the positive plate and carry them to the negative plate. And carry them to the negative plate. So, that means in order to form this structure, as if I need to plug one electron from this side and then I put it here, right. This is the way, suppose I am making my capacitor where I am putting some kind of charge distribution. So, plugging one electron from this side and then put it here in another plate. So, in order to do that, one has to do the work. So, that means in order to do it, one has to one has to do the work. To charge the capacitor up to a final amount Q, because so this is the finally Q is the amount that the charge should have in the left hand side and right hand side. So, one has to the point is one has to do some work to charge up the capacitor. Now, let us some intermediate. So, that is the concept. So, based on the concept we should going to calculate what is the amount of the energy stored here, because whatever the work we will do, that is the eventually that is the energy that should store in this capacitor. So, suppose some intermediate state, the charge on the positive plate is say Q2, some intermediate state, some the charge of the positive plate is say Q. So, in that case the potential difference Q. So, the charge at the, so I should write the charge on the positive plate at some intermediate state, it is Q. So, that leads to the potential difference Vi is Q divided by the capacitance C. Vi is again some intermediate potential. Okay. So, now the work done required for the next piece of charge. So, now after that, so let me write it now, the work done to transport the next piece of charge dq is, because already I have a potential at intermediate state. So, now after that if I now bring a dq amount of charge, then the amount of work done is simply dw is equal to whatever the charge I bring against the potential Vi. So, this is simply q divided by C dq, because q divided by C is my Vi, the intermediate potential, where q is already there. So, now we are in a position to calculate the total work done to bring all the charges. So, W is integration of dW, which is simply 0 to the total charge and then q divided by C and dq. So, this amount is simply half of 1 by C then q square. So, simply q square divided by 2C. But q again in terms of potential, q again for capacitor, q is equal to CV, right. So, that basically gives us the expression, the total work done is half and q is equal to CV, once you will cancel out. So, half C V square, that is the amount of energy, eventually the energy stored in the capacitor. Okay. So, we can do one simple example. So, assume that it says the charge q on the parallel plate is constant, constant. Now, find the work done against the electrostatic force to increase the plate separation from D1 to D2. So, the problem is straightforward. So, I have one parallel plate capacitor where this distance initially was D1. Now, I need to increase the separation of this parallel plate capacitor from D1 to D2. The question is, what should be the work done? Right. Now, we know the energy of the system, and then from that we can simply calculate it, because the energy of the system is simply half C V square, and that is simply q square divided by 2 C, and C again, because I need to change the separation. So, I need to write C in terms of the separation D, A divided by D, that we calculate. So, from here I can write that it is simply q square D divided by 2 epsilon A. Now, the charge is fixed, epsilon is constant, A is also fixed. So, the amount of work done delta omega, delta W is equal to q square divided by 2 epsilon 0 A. So, whatever the energy we have previously, and now whatever the energy we going to have. So, D1 minus D2. So, that is the amount of energy now we need to have, and that is the, in fact that is the amount of work done you need to do to make this separation from D1 to D2. So, that is the result. Okay. After that, now we like to understand what is the meaning of dielectric. That discussion we should start now in today's class. So, the next topic, important topic, is dielectric. So, that means electric field in, actually we will going to discuss the electric field in matter, and this matter is dielectric. So, the main topic is under electric field in matter. We already discussed what happened when the electric field, when you have the conductor under some electric field. Now, we will going to do the same thing, but now our system is different, and that is called the dielectric. So, dielectric system, unlike conductor, it does not have any free electron. That is the major difference between dielectric and conductor. So, what happened here in dielectric? All charges are attached to specific atoms or molecules. So, there is no free electron, and so what happened that so let me draw it here. So, suppose this is a dielectric system, dielectric atom or molecule, and the plus charge and the minus charge, they are superimposing each other. So, this is plus, and the entire, so this is a neutral atom, and in the neutral atom what happened, this is a natural atom, and in this natural atom what happened, the entire, the electron cloud is, over electron cloud we have a positive charge here plus q, say, and this entire cloud is distributed in such a way that the charge density, charge center of the charge minus q and plus q, they are superimposing to each other. That is for natural atom. Now, what happened if I put this dielectric system under some electric field? Suppose I am putting some kind of electric field here for this system. So, suppose I have some external electric field, and what happened that it induces some dipole. So, the plus charge and minus charge, there will be a separation, tiny separation. So, I should have a distortion here, say like the this cloud, electron cloud, and say the plus charge will be shifted to some place here, and I should have some effective negative charge sitting here. So, there will be a charge separation, and that leads to some tiny dipole. So, that is the concept here. So, we have a charge separation here like this, and some tiny dipole will go to form. So, here the atom now has a tiny dipole moment. And we call it P. So, now my Q minus Q is sitting here and my plus Q is shifted under the external electric field, and that is why this leads to some dipole moment, tiny dipole moment, P, and P is normally proportional to the applied electric field. So, I can write that P is equal to some constant and alpha and electric field. So, this constant alpha is called in this case the atomic polarizability. Because an atom, when you apply the electric field, normally the polarization is proportional to the applied strength of the electric field, and we are having a atomic polarizability. If I look the entire picture, let me draw the entire picture what happened for a bulk material. So, suppose we have a bulk material like this is a dielectric material, and under the external electric field, suppose this is the external electric field I am having here along this direction. So, what happened? The dipoles are distributed like this, tiny dipoles will be formed in this way. There will be a charge separation, and as a result of this charge separation, I have tiny dipoles. They lined up. This dipole will going to lined up with external electric field. So, I should have a plus sign here, and minus sign here. So, that is the macroscopic dipoles are lined up here. No, this is not macroscopic, this is the microscopic dipole. So, these microscopic dipoles are lined up like this. So, now we should put the concept of polarization. The polarization is dipole moment per unit volume. So, that is called the very important term called polarization. Which is defined as P, this is a vector quantity, and that is dipole moment per unit volume. So, mathematically if I want to write this polarization, that should be under the limit delta V tends to 0, 1 divided by delta V, whatever the dipole moment we have, all the dipole moment, I should have a summation over it, and that should be the form. Now, quickly let us calculate the atomic polarizability, not the bulk, but the atomic polarizability. So, next thing I will calculate the atomic polarizability So, this is the structure we have, and this is the external field I apply, and there is due to that. So, there is a separation, right, of the charge. So, the total charge, say Q. So, under the external electric field E, what happened, that there will be a charge separation as I mentioned here, and an equilibrium situation, the external field and the field produced by the electron cloud at D, they should be identical. So, whatever the external field and due to the charge separation, whatever the field, they should counteract, and at the equilibrium they should be equal. So, that is the condition. So, at equilibrium, I have the external field should be equal to the field produced by the electron cloud at D, because there is a separation. So, it should produce this electron cloud should produce some electric field here, and that should be these two should be equal. Okay. So, now we will going to use the straightforward form, that whatever the field it will going to produce here at D, that I need to calculate when we have the total charge. So, it is like a electrostatic problem, straightforward electrostatic problem, we will going to use that concept. So, the field at a distance D, how you calculate? So, I will just draw like a Gaussian curve here, the Gaussian surface, and our aim is to find out what is the field it is producing. So, that E. So, E. So, if this is D, so Gaussian surface suggests that I should write 4 pi d square, that should be the total charge enclosed. Mind it, the total charge over this entire volume is Q. So, the volume charge density sigma should be Q divided by, if it is a radius of A, then Q divided by 4 by 3 pi A cube. So, the charge enclosed divided by epsilon 0. So, now what is charge enclosed? Charge enclosed is the density multiplied by this volume, and this volume is simply 4 by 3 r d cube divided by epsilon 0. Now, let us put the charge value of the charge density, then it should be 1 divided by epsilon 0, rho is total charge Q divided by 4 by 3 pi A cube, and then multiplied by 4 by 3 pi d cube. So, 4 by we will going to cancel out. So, this will going to cancel out, and eventually we have E we have q divided multiplied by d cube divided by epsilon naught a cube multiplied by 1 by 4 pi d square, which is already here in this side. So, eventually this value becomes q total charge q multiplied by d divided by 4 pi epsilon naught and a cube. Now, the atomic polarizability, we know how to calculate the dipole moment. So, P dipole moment is charge, total charge multiplied by the distance d, and electric field is equal to P and q d sitting here. So, it should be P divided by 4 pi epsilon 0 a cube, because this quantity is nothing but my small p. So, here this is equal to again alpha p, where alpha is my atomic polarizability. So, from that I can write that alpha is equivalent to 4 pi and 4 pi epsilon naught sorry. So, P is this is alpha minus 1, because the formula is P is equal to alpha E. So, E is equal to alpha inverse P. So, what I calculate is alpha inverse is 1 by this. So, alpha is equal to 4 pi epsilon 0 a cube, and that is eventually the value. So, I can write in a different way also. I just put 4 by 3 pi a cube and then 3 epsilon 0. So, that gives me the volume. So, it is simply 3 epsilon 0 and the volume of the system, or volume of the atom. So, alpha is roughly the atomic polarizability is simply alpha is equal to 3 epsilon naught and then V, where V is the volume of the atom. So, this is the way one can calculate the atomic polarizability. This is a technique. I mean, just use the standard tool we have, the tool we use here in form of Gauss's law, and then we can find out what is the value of the atomic polarizability. So, today I do not have much time, so I would like to conclude here. So, in the next class I think I should discuss about the susceptibility, more about the susceptibility and susceptibility tensor, because here we see that the P, I write the polarization, let me, so polarization is proportional to the electric field. So, that means if I write this equation, that is essentially means that the P x component is proportional to the E x component and P y component is proportional to the E y component, and P z component of the polarization should be proportional to the E z component. So, each component wise they are proportional. So, then only I can have a relation like this, and not only that, this proportionality constant is same for all the cases. For E x, E y, E z, this proportionality constant should be same, but normally this is not the case. So, we can have a system where P x does not only depends on the E x, rather it can also depends on E y and E z, and that gives rise to something called the the susceptibility tensor or polarization tensor. So, that thing we will going to discuss in the next class, and also try to understand based on this concept of dielectrics, what is the called the bound charge and bound current, bound charge and surface bound charge density and bound surface bound volume charge density and bound surface charge density in the form of polarization. So, with that note, let us conclude today's class. So, thank you for your attention and see you in the next class.